Hello, class. In the last section of Chapter 5, we will be discussing perpetuities, which, as you can read from the slides, a perpetuity is just an annuity that does not end. So, just to review the concept of annuity, an annuity was just a series of payments over a particular time frame. So, say, for example, over 3 years, if we're going to make a monthly payment, we're going to have 36 payments of, say, $200 or whatever, where R is going to represent the number of payment or the amount of the payments, and capital N was the number of payments in that annuity. Where we discuss, well, what's the present value, what's the future value of an annuity, where an annuity, recall that the present value was always less because we're not taking into account the interest that accrues over the entire life of the annuity, whereas the future value is more because it is taking that interest into account. And as the book demonstrates with its diagrams, we're kind of looking at present value as what's it today as a negative effect, where each of those payments is worth a little bit less due to the negative exponent, and future value is worth more because each one of those is magnified by the compound interest positive exponent. And that's how I organize it in my brain in terms of remembering present versus future value. Really, the only difference is negative exponent versus positive. But a perpetuity does not end, which adds another confusing element to these problems. And there's some things that are a little bit hard to really wrap your head around, which in this video I want to focus on the mathematical side of the present value of an annuity, sorry, of a perpetuity, where the name indicates that, that's, what in perpetuity means is that it's not going to end, like perpetual. So if you're trying to remember these terms, that's kind of the idea of the name. Um, but one thing about perpetuities is that we're not going to be trying to find the future value because no such thing exists. Since it's going on forever, the problem is thinking about its future value. We don't have a time to look at. Like with an annuity, we know it stops at some time, and we can look at what's the value at that point in time. But with a perpetuity, it's going to go on forever. We could think of it as, say, we're putting in $200 a month into a perpetuity. Basically we'd be doing that forever. There is no future value because, and this is the hard thing about forever is I'm gonna literally do it. I can't do it forever. We're going to die. But most of the time, perpetuities are thought of not as something we're investing into, but a lump sum that will be an ongoing payment forever. And one of the things about amortization that I wanted to reiterate, that I don't know if I made quite clear in 5.5, was that really an annuity and amortization are the same thing. They're just kind of different ways of looking at it. An annuity is something where we typically think we're investing into it, and at the end we're going to have amassed a very large amount of savings. Uh, where a amortization is like we're upfront paying a lot of money for a loan, and then we're slowly paying it off over time to nullify it. But both of those are kind of the same idea. We're putting in a certain amount of money over a certain amount of time. If we're investing X dollars per month, we're building up to this larger lump sum. But amortization is much the same thing because we're starting with this massive lump sum that we're borrowing and we're slowly paying it off. It's the perspective. For a bank, uh, it, a loan is just like an investment, and up front they're loaning us some amount of money, which is like the present value, um, of an annuity, which is really the amortization formula was exactly the same as present value versus future value would be what we'd use if we were trying to figure out how much we'd get if we were investing. So what I strongly recommend is you think about the time frame, because what's important to try to resolve is this a present value or future value problem? Because that's the only difference in any of the formulas that we've been discussing. But anyways, we can discuss the present value of a perpetuity. So imagine that we were putting $200 a month into something forever. So we could kind of imagine, okay, $200, $200, $200, $200 ongoing, never ending. But what we could imagine is, well, what's the current value of that? Like each payment we could trace back to today, how much money would I need to do that? And this is something where if you're thinking about it, it might not seem to make sense because if I'm paying $200 forever, it doesn't make sense that there would be some number that could ensure a literal payment forever, but there is. And that's kind of the interesting concept within a perpetuity. So let's get into the math. So if we're looking at A, remember A stood for the present value of an annuity. So we're just going to use the same thing for a perpetuity because it's the same thing just going on forever. We could imagine each payment's present value in the same way we did for an annuity, where after 1 month, that first payment, and remember this is all about an annuity, an ordinary annuity, not an annuity due, which I discussed that in a previous video, but we're just assuming that we're making our first payment after 1 month, not currently. But the first payment would be reduced by 1 month's worth of interest because we're examining the present value. The second would be reduced by 2 months, and so on. Each payment will be divided by 1 plus the periodic interest rate a number of times based on the present value of that money. And the kth payment will be reduced back by k time frames. But basically, this is going to keep going and going and going. So if we're looking at the sum, the net present value of this perpetuity, we'd have, well, this is the first, the second, the third. And what we'd have instead of a finite series where we briefly discussed this back in chapter 1 when we were talking about sequences and series. A finite series is one that has a fixed number of terms. An infinite series is one that goes on forever. And I briefly discussed that you can have an infinite series that is finite that adds up to a fixed number. And the example we did was slicing a cake. If you remember, I talked about if you think about taking a cake and cutting it in half, there's no limitation to the number of times you can cut it in half. You could represent it as an infinite series: 1/2, 1/4, 1/8, 1/16, 1/32, 1/64, and obviously at some point in actuality, that's going to be impossible to do because the cake will become too flimsy. But theoretically, there is no end to that series of fractions. And if I continue to slice that cake, another question is, will I ever and eat each of the slices? Will I ever eat the whole cake? And that's kind of the idea of infinite. Infinite's a hard thing to know, but the limit of that progress is the whole cake, and the sum of an infinite series of actions, like slicing a cake in half, could be a finite number. In that case, it was 1 because the whole cake we would eventually eat. Technically, we don't eat the cake if we stop, but if we keep going infinitely, we would reach that pattern. Anyways, my point here is that actually this infinite series of present value formulas is actually a finite number. It's a specific number, and at the very end, I think this will make sense better. But let's work on the math and focus on infinite series. So returning back to the geometric series idea from annuities, all of the math that we did to talk about what's the present value and the future value of an annuity was based on this geometric series formula, which was just that when we have a geometric series such as this, it's geometric because we have a first term and each term is multiplied by the same thing. It's multiplied by 1 plus p to the minus 1. So given that there's a predictable pattern, there's a predictable sum when there's a finite number of terms. And the nth partial sum formula gave us the sum of those n terms, which was given by this formula. And this was used to derive the formulas we were using for present and future value. And it's a very important mathematical idea. But another thing about this was for a fixed number of payments. Another thing that we could consider is, well, what happens if we don't have a fixed number of payments? What happens if this continues indefinitely? And it turns out there's another pattern. It's actually even simpler to where the progression of the geometric series heads towards. But considering a case where n goes to infinity, in that instead of saying having 36 payments, let's say we had a million or a billion, basically this did not stop. What would happen if n trended to infinity? And in calculus, this is often how we write it, where meaning that we're just going to examine what's going to happen forever. But what actually happens to r as I head to the nth power is it will become 0 and become a much simpler formula. And this is because in a financial situation, r, which is, just to review, when we're talking about a geometric series, it's the common ratio of these terms. R is it is going to be the periodic, 1 plus the periodic interest rate of our account, right? If we're looking at the common ratio, it's 1 plus p to the minus 1 power, within a perpetuity. And if we look at those numbers and what those do, sorry, let me go back to my other. Actually, I can put it right here. Um, Basically, let's say our periodic interest rate was just 1% or whatever. I don't know. I'm just gonna use 1%, not 10%, 1% for my argument. That would be to the minus one power, and this would be the common ratio in our geometric series, aka 0.99. But if we think about what happens if I keep multiplying by that, uh, that's kind of the idea is what happens if we do r to the nth power? What happens if we exponentiate that number 36 times? This would give us the r to the n power. But if we were to keep doing that, if we were to take 0.99099, I'm just going to round it for the sake of easiness. What if we were to do that 100 times? Or what if we were to do that 1,000 times? What if we were to do that 1,000,000 times? And this is the idea that we discuss a lot in calculus, which is the idea of infinity of doing it something forever, which is what we're trying to consider as we look at a perpetuity. But the limit of an exponential function with base less than 1 is always going to be 0 if you do it forever, meaning that regardless of what that interest rate is, assuming it's not a negative interest rate, which is kind of a funny consideration, but would always trend to 0. So returning back to the PowerPoint, this is the final summary here is that in a geometric series dealing with any financial matter, if I were to go to infinity, this would head to 0, and that greatly simplifies our nth partial sum formula. And this is a very well-known formula for what we call the sum of an infinite geometric series. Infinite geometric series always have a very simple infinite sum, which is the first term divided by 1 minus the common ratio. And basically what we could use is we could use this infinite geometric series formula to find the present value of a perpetuity quite easily. Since it is again a geometric series, it is just infinite instead of finite. So putting the math back to this, the present value of the perpetuity is the sum of all of those infinite number of payments. And I should have written plus dot 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 here. I just forgot to on this slide. But basically, we're imagining instead of a series going n of n particular payments, we're taking an infinite series of payments where r is the first term and 1 plus p to the minus. Well, technically, r 1 plus p to the minus 1 is the first term. So I didn't quite colorize this properly, but this is all right still. Anyways, and then we have the sum of 1 plus p to, like the first term, if I plug in 1, what that would give me is 1 plus p to the minus 1, which would give me this. The second term would be plug in 2, 3, 4, 5, but it would go on forever. This should continue. I just forgot to write my dot dot dot. Anyways, the only difference from an annuity was that we're not stopping at n, we're going to infinity. And basically, the sum of an infinite series, instead of using that nth partial sum formula, we're going to be using this much simpler infinite series formula to find the present value of a perpetuity. Where it's just the first term of the series, this one, divided by 1 minus the ratio. So 1 minus 1 plus p to the minus 1. And this should give us the present value of the perpetuity. And also this greatly simplifies to give you the formula that's in your packet. So of course you could just use the formula in the packet to solve these, but the point of this video is to try to understand why. What's the sense behind these weird formulas? Because without the why, we're just memorizing things and we're never going to ever remember it. But basically, if we take that formula, the first term over 1 minus the common ratio, and since this is a minus 1 power, we could always flip that to the bottom, which is what I did in the slides, r over 1 plus p to the 1 plus 1 plus p to the minus 1 power. Actually, if we distribute this term out, this greatly simplifies almost amazingly. But what we get is 1 plus p times 1, which is 1 plus p, then 1 plus p times 1 plus p to the minus 1. And notice that this term, this just means 1 divided by 1 plus p. If I do 1 plus p times its reciprocal, It's basically this would mean 1 plus p divided by 1 plus p. That's just going to give me 1 and minus because it's this times that, but it's negative. So what I end up with is 1 plus p times 1 minus 1. And 1 minus 1 is of course 0, which cancels and leaves us with r over p. So in summary here, the present value of a perpetuity is the amount of the payment divided by the periodic interest rate, and that will give you how much it's currently worth. And now coming back to any sort of sense, um, so what is it that we're going to solve? I think when we do an example, it will make more sense. But basically, what we're doing is we're figuring out what amount of money up front would ensure something lasts forever. And basically, how this will work is that we need enough money up front that the interest growth makes those payments. Because you could imagine if you have enough money, it's going to grow an amount by the interest rate. So say, for example, we could create an account that grows by $200 every month. We could then take the interest out as the payment for the perpetuity, but the balance will never change. So you can imagine an account with a balance of, say, $1 million every month, and the amount of interest is going as out as the payment. And basically, we will never run out of money because of the interest growth. Now, obviously, if the interest rate or something horrible happens, it might not continue forever. But if we were to have a interest rate, which in most times, you can usually have an account which is growing at a decent interest rate, you can ensure something lasts forever.